Algebra Qual 2020, August 2020, rings and fields number 5, part 2, take 2. So f of x in Q is irreducible over Q. Since it's irreducible over Q and Q is characteristic 0, that means that f of x is separable. So since we have a separable irreducible polynomial over Q, when we look at the splitting field K, then we know that K is Galois, K over Q is Galois. So then the degree extension of K over Q is equal to the cardinality of our Galois group, and we haven't talked about this stuff in red yet, so we'll do that in a second. So what we're going to do is we're going to let beta be a root for f of x in K. We know it's equal to 0, and we know that the Q adjoined beta extension is going to have degree beta, and the degree of beta is the degree of the minimal polynomial of beta in Q polynomial. Okay. So then the minimal polynomial has to divide f of x because beta is a root. So, but because f of x is irreducible, it can't have any actual factored terms or any polynomials of degree 1 or more or anything. So that means that f of x is just some scalar multiple of our minimal polynomial, which then means that this degree extension, this degree extension is P. It's the degree of the minimal polynomial. The degree of the minimal polynomial is the same as the degree of f. The degree of the minimal polynomial is f. So then, what we can do is we can look at a tower of fields where we have finite extensions adjoining roots that we do not have yet. The very first extension is going to be of degree P by this argument. So then the extension, or the degree extension of our splitting field over Q is going to be some multiple of P. And if it's some multiple of P, then that means our Galois group also is of some multiple of P in cardinality. Okay with this? Mm-hmm. Okay, cool. Whew. Now to do the other part of the proof. You were so right though, that did need more arguing. Okay, so now we have G is going to be the Galois group of our splitting field over Q, and we just argued that the degree of G is P times some B, where B is just another constant, or just some integer. Because we have a finite group, we can find a subgroup H, subgroup of G. The cardinality of H is equal to P. It exists somewhere in there, cosets. And then that means that there exists some element, we're going to call it G, in H, where the order of G is equal to P. So we have found an element in G, which is of order P. So we have G in G. We know that G is really, or can be thought of as a subset of SP, the symmetric group of P elements. So we're just going to let G be equal to 1, 2, 3, ... all the way up to P. So G is a P cycle, order P. Cool. So far, still good?
So you're constructing an isomorphism between the Galois group of K over Q and SP?
Not yet.
Or a subgroup of SP?
Yes.
Okay.
That part is yes. It is a subgroup of SP. Mm. But we're going to show that it has the generators for all of SP. Yeah. Same thing, different words. Fun. Okay. So then we have some alpha in the complex plane, in the complex numbers, where alpha is a root, f of alpha is 0, and then if we consider f of its conjugate, because f is a polynomial, we're going to get the conjugate of f alpha, which is just 0. So then alpha and alpha bar in C are two of our roots. And what we can do is we can look at the fixed field for alpha, where we have a Q adjoin alpha, not the fixed field of alpha, the degree extension of alpha over Q, which is 2. And what does that do? Well, in G, we can get another subgroup which correlates to this guy. Yeah. So then we're going to get our, let me call it, I guess I. We have I subgroup of G, who, which way does it go? Is it the cardinality is 2? Or, yes, yeah. Where it's is equal to 2, which means we have some transposition 1, 2 as an element of I, as a subgroup of G. That's what it is. So then we're going to have, we'll call it, instead of G, I'll just use H. H, element of G, H is equal to 1, 2. So it permutes the roots, the complex roots there. Okay. So then we have a transposition and a P cycle. So then what am I saying? Every 2 cycle is conjugate, and we can permute our elements each step of the way. We can permute or conjugate however many times we need to get all the transpositions. We can get every transposition in SP by conjugating G and H together, which means that G has all the transpositions, so it is SP. H and G generate G and SP. And that's the argument.